name is Liz Vivas. I am an associate professor at the math department at Ohio State University. I've been at Ohio State since 2014. I completed my PhD at University of Michigan, and after that I did postdocs at Purdue University, Brazil, and France before coming to Ohio State. I'm originally from Peru. When I was younger, I definitely was very interested in mathematics. I love puzzles, problems, but I also like other things. I actually started my undergrad in engineering. So I did engineering first, which had a lot of math classes, which I loved, and that's what I chose engineering. And so that's when I realized that I only liked math classes. I decided, okay, maybe I should pursue a master's first. I guess I wasn't very familiar with the academic circle in general. My parents are not academics. And in Peru at the time, it was not very common to have an academic life. So I was not aware that mathematics could be a career. In fact, I thought people who did mathematics then ended up going to be high school teachers in mathematics. That was the most common career path in Peru. But yeah, I found out along the way that it was possible to do research in mathematics throughout, and that sounded really appealing and really fun. I like the excitement of discovering things. I like very much the precision of mathematics. It's not, having said that, it's not a very precise science in many ways, but once things are cleaned up, it looks very nice and neat and easy to follow in some ways. Say you're trying to uncover some kind of hidden structure between two different things, and you kind of can see that it's there, but it's not clear how they are really similar or what kind of connection there is there. So in that respect, I mean, it's not very precise until one makes it even more precise. First, one has to learn definitions and what math people are working on. That takes a long time, and that's sometimes like a very big barrier to understand what's next. Having said that, I think that a lot of what math research is about, it's really about playing with concepts and definitions and looking for connections or trying to solve a problem. I think there's a lot of research, as people think it is like going to a library, open a book, finding out some bibliography that can be helpful. It is in some ways similar to that, but instead of going into a library and opening books, well, sometimes you're looking at other papers, sometimes you're thinking about in your own head, what could it be, this connection from this thing with another or this answer.
In the next section, Dr. Vivas talks about functions. You might remember about functions from high school. A function is a relation between two sets of objects. In the scenario Dr. Vivas refers to, these objects are numbers and the function is given by a formula. For example, here the function f of x equals 2x plus 1 relates every number x with the result of multiplying that number times 2 and then adding 1. Thus, f of 1 is 3, f of negative 2 is negative 3, and f of 3.14 is 7.28. A function can also be represented by its graph. Here you are seeing the graph of our previous example, f of x equals 2x plus 1. In school, we focus on nice functions, but functions can be very weird too. Mathematically, we study certain characteristics of functions that make them quote-unquote nice. For example, roughly speaking, a continuous function is one where the graph doesn't have any gaps. You might have learned about derivatives too. Differentiable functions are those that have a derivative. This might be surprising, but not all functions have derivatives. Functions that are not differentiable are easy to identify from their graphs because, again, roughly speaking, they have pointy peaks. An analytic function is like a super differentiable function. If you find its derivative, this new function, the derivative, will also be differentiable, and the derivative of the derivative will be differentiable too, and so on.
When one thinks of functions, there are functions that are very complicated and very weird and non-continuous. But then if one starts asking for a little more of your function, you can ask for functions that are differentiable, that they have derivatives everywhere, etc. And one very nice class of functions are analytic or holomorphic functions. These include all functions that maybe you have thought of, like all polynomials or sine and cosine. All these functions are analytic, exponential. And these functions have really nice properties. And it turns out that it makes a lot of sense to define them not into real numbers, but into complex numbers, which is an extension of the reals. And in this way to extend these functions to all these complex functions, to all the complex numbers, one finds very nice structure for these functions and lots of very nice behavior. And so all this field is called complex analysis because one basically analyzes the functions that are defined as complex functions. Well, a complex number, it's basically an extension of the reals, and as I said, it's mainly because we want to solve every equation. So we know how to solve 5x plus 7 equal 10. We pass 7 to the other side and divide by 5 when we get an x. But say we want to solve x squared plus 1 equals 0. We do not have a solution on the reals to solve this problem. We will have to get x squared equal minus 1, x equals square root of minus 1. And this is not a real number. There is no real number whose square added 1 gives us 0. So we construct a new number called I, which is the complex number. And then basically it's kind of amazing and a miracle that just using this I new number, every solution of an algebraic equation has, every algebraic equation has solutions in the complex number.
In your high school algebra courses, you learned that some quadratic equations don't have a solution. Well, now with this I number that Dr. Vivas is talking about, all those and any possible equation you can invent combining a variable, positive integer exponent, coefficients, and the operations adding, subtracting, or multiplying, any of those has a solution in the complex number.
Function going from space to another space, C to C. And we are just going to study what happens if I take one point and I apply this function to this point. And then I apply the function to this output. And then I apply this function to the new output of this and see where this point is going. This is what we call an orbit of a point. So let me say, for instance, an example, like if I just think about the square function, I start with 0 and I square it, I get 0, and I square that number and I get 0. That will be an orbit. Or if I start with 1, I also get 1 again and 1 again. But I can start with other numbers, like 0.5, and we can square it and we're going to get 0.25, and we square it again and we're going to get, I don't know, 0.0625 maybe, or something like that. And so you see that the orbit is changing, and in fact it is approaching 0. So one type of problem that I have been interested on is understanding or extending a theorem in one complex dimension. So this is one complex. So these functions go from C to C. And the type of functions that we have are functions that start being almost the function itself, but then I perturb with a higher degree term. Say something like this. And so there is a theorem actually of the 1920s. These are two French mathematicians that explain that for any map of this type, the behavior of what happened to the orbits at 0, it's completely well understood by just looking at the next term that is not the identity term. So in this case, I'll look at this one. you look at the smaller of all of those, in this case is 2, and so they explain that you will have 2 petals. Let me draw them this way. And on these petals, every point, the orbit of every point is going towards 0. Every point that I take on this complex plane will map towards 0. And 2 repelling petals, which the opposite happens. At every point from here is actually coming from somewhere outside. So this is called as the Flower Theorem because of the petal terminology. The question is, what is this in 2 dimensions? And by that I mean, say, a function from C2 to C2. So how can we think of a function from C2 to C2? If you just think about it as 2 variables, which each one is a complex number. And the same idea, what happens if I have C, W, and then I perturb by something. Say I perturb by C squared plus W cubed, C cubed minus W squared, or something like that. What is the petal theorem in this context? And this is still something that we don't understand completely in many, many cases. Many functions on this respect do have some kind of Flower theorem or not. So I'm interested on these kind of questions for this for this theorem, to extend this theorem. So say C plus Z to the 4th. So then you're gonna have, it's this number again that tells us. So before it was 2, and so that means one take 1 less than that. So this is 4 minus 1, so it's 3. So there should be 3 kind of attracting petals, and then 3 repelling petals. Oops, this should enter. And this brown picture should have. So that will be for this case. You always look at this number and you take 1 less, and that is going to tell you how many attracting, in this case these brown ones, and how many repelling, in this case these ones over here.
As we said before, complex numbers are not on the number line. Instead, they can be represented on a Cartesian plane. We write the real component as the horizontal coordinate and the imaginary component as the vertical coordinate. For example, the complex number 2 plus I corresponds to the point 2, 1, while 3 minus 3i corresponds to 3, negative 3, and 4i minus 1 is negative 1, 4. The Flower Theorem works for polynomial-like functions that take a complex number as input and give another complex number as output. The function must include a linear term, the variable itself with no exponent. The function can include more terms with higher exponents. Once you have your function, you have to look at the next smallest exponent. Whatever that number is, the orbit of the function will have 1 less petal than that of each type. There are 2 types of petals, attracting petals and repelling petals. Say you take a point inside one of the petals. Remember that this point is a complex number. You then plug it into the function. Whatever the result is, you plug it into the function again. You get a result and plug it into the function one more time. You repeat this process over and over. What the Flower Theorem explains is that if the point you started with was in one of the attracting petals, then after repeating the process over and over, you will eventually get to 0. On the other hand, the points on the repelling petals, after plugging them into the function over and over, will eventually end outside the petals where they start. The shape, position, and size of the petals changes depending on the specific function. What Dr. Vivas is investigating is how this Flower Theorem changes when the function is a multivariable function, meaning that instead of taking as input a single complex number, It takes 2 or more, and it also outputs the same amount of complex numbers. As in this example of a function from C2 to C2, which takes 2 complex numbers as input and returns 2 complex numbers. Notice that there's a formula for each output, but both formulas include the input values plus something else, as the Flower Theorem requires. The problem Dr. Vivas and other mathematicians are trying to solve is if these multivariable functions also present attracting and repelling petals or not, or perhaps in some cases they do, but in others they don't.
I like biking a lot. I'm not a serious biker. I bike school from my home. I like activities, being outdoors, being outside. I like hiking and biking. I have 2 little kids, so it's harder sometimes to bike and hike with them. And besides that, I enjoy reading a lot and knitting and crocheting during the winter time. That's my outlet.